Today we're going to continue our discussion on longitudinal stability. But before jumping back into that, I just want to mention something about wing design I failed to say. We've been looking a lot at lift distributions, lift coefficient distributions, and some of those trade-offs. It's important to keep in mind that, well, I guess really a danger in many engineering analyses, if we look at just one thing, we may optimize it for that, but forget about some of the other disciplines. So in this context, one common thing I see is sometimes a lot of designs come out with the Hershey Bar Wing, right? An untapered straight wing. And that can work fine for lift distribution, give you a good lift coefficient distribution, but that's very rarely an ideal design. That's why you almost always see most airplanes will have a tapered wing. And there are many reasons for that, but for one, the lift distribution naturally has to go towards zero at the tips anyway, so we don't need as much chord there. And having large chords at the tip is going to add weight, right? It's going to add weight in part because there's more area, but also because that's more mass that's further away from a root, right? So there's going to be the roots, there's more bending weight. So weight is a problem. Also more wetted area, right? If I don't need that much chord out at the tip, then I'm just adding more viscous drag. Those are some reasons. So we generally are going to have a tapered wing, at least some taper, so we can shed some of that unnecessary weight and drag. We can't be too extreme though, because as the chords get really small, your lift coefficient of the tip is going to go up, and then you're going to get closer to a tip stall. You can avoid that by twisting the wings down, right, using washout, but that's going to compromise your lift distribution potentially. So there's these trade-offs, right, in trying to reduce chord, to reduce weight, and you can find a good solution, right? One that's tapered, still has a good lift distribution, and still avoids tip stall. This is quite possible, but it takes a little bit of iterating. So just wanted to mention that as you're thinking about iterating on your design going forward. Okay, so let's continue with the longitudinal stability. See if you can remember what we talked about last time and what some of the key takeaways were. One major takeaway that you'll want to remember as you work on your design is that we discovered that we need our center of mass to be in front of our aerodynamic center. Right? That was a necessary condition for stability, that having that center of mass forward meant that as the angle of attack increase, because the lift is behind, here's the center of mass, let's say the lift is behind, the angle of attack increases, that lift behind levels me back out, right? Whereas if my center of, or aerodynamic center was behind or in front of my center of mass, I'd increase the angle of attack, the lift would increase, and I'd just keep flipping over. So that's a necessary condition for stability. We also saw that for a wing, it can be a bit challenging to also provide trim, meaning zero moment, steady flight, because the wing or the lift is behind, that creates a negative pitching moment. So this is behind, it provides a negative pitching moment wanting to pitch down, but the airfoils are generally going to have negative pitching moments also. And so those are both acting in a negative direction and don't counterbalance each other. We saw that for a wing, if we had just a wing, there were some ways around that by sweeping the wing or using an airfoil with a positive moment. That's a less efficient but possible solution. Today we're going to talk about a more conventional solution. And that is to use a tail. Okay, so like last time, I'd like you to try this first. There's a wing, there's a tail, there's a center of gravity, and then there's an aerodynamic center. See if you can place these, figure out how this should work. How does a tail and a wing work? So just pause and give this some thought. Draw some of these diagrams. Okay, so let's just draw it generically here. I'm not assuming any particular directions. I'm just going to assume positive, right? So the lift, I'm assuming positive. I'm assuming positive X's. I'm assuming a positive moment, although as we saw, this wing or this moment of the wing is pretty much always going to be negative. I've just drawn it positive just for the, just to be generic and let the signs come out, but it's almost always going to be negative, okay? So last time we did the math first and then we kind of did it physically. Let's this time just do it physically and then maybe work through the math. So here's my center of mass or center of gravity. The moment generated from this moment we said is going to be negative, so that's going to want to nose me down, right? Nose down. The lift of my wing, that's going to be up, and we already said this has to be back for stability. The aerodynamic center isn't exactly at the lift of the wing, it's going to be somewhere else, but it's going to be close to here. Okay, so for this discussion, let's just say it's behind here. That lift, if we do R cross F, right, that's also creating a nose down moment. So both of these are going to cause my airplane to nose down. So if I wanted a tail, if I had this lifting surface back here, I need to create a moment in the opposite direction, a positive moment. And to do that, if we look at the direction, R cross F, I actually need my tail to lift down. Okay, so this is going to be, this LT is going to be negative. I need to generate a negative force at the tail. So this is a traditional solution because it's not too hard to do. It's not necessarily the most efficient. A flying wing, if done well, can be more efficient because now, you know, we're generating negative lift. And so to compensate, we're going to have to generate more lift at the wing. That's going to also increase our induced drag. This tail is adding some wetted area. It's adding skin friction drag and pressure drag. So there's some penalties to be paid. And of course, I have to somehow connect this tail. I may have a longer fuselage or a boom, and sometimes I may have that anyway, but not always, right? So I'm generally having to pay some penalty in weight and drag to use this tail. But because the tail is so far back, or can be far back, right, I don't have to generate a big force because I have a big moment arm, right? If we do that R cross F, a big moment arm can give me a big moment, so I don't have to have a lot of downward lift, you know, maybe let's say at most maybe 5% of the total lift in the negative direction. So, but of course, going further has its trade-offs, right? The further away it is, again, the more surface area and weight I needed to add to connect a tail that's further back. So there's going to be some trade-off that occurs. Okay, but this is the main takeaway though for a tail is that we can do this. We can provide that trim. We've already got stability because our center of aerodynamic center is behind, but to provide that stability, a moment that goes the other direction, we need a force, a lift that goes downward towards the back of the airplane. Okay, and again, there are compromises, not necessarily as efficient as a flying wing, but generally easier to design. Okay, so let's do the math, and we're going to do a somewhat reduced version. We're going to ignore drag because that has very little contribution to the moments. We'll just assume small angles, no offsets here. And we're going to ignore any moments from anything besides the wing. Let's assume that's all wrapped up into this one moment, and that kind of could include moments from the fuselage. The tail generally doesn't contribute a pitching moment because it's almost always a symmetric section. So for this simple analysis, we'll ignore that. So in that case, we'll take moments about our center of gravity. That's going to be the moment of our wing, and really that's going to be negative, right? But again, I'm just going to use all positive values here and let those come out. But typically that's going to be a negative. And then using the directions I've shown, right, the lift is going to give me a negative, it's going to be minus XW, LW, and same with the tail, since I've drawn it in the same way. It's just going to look like that. So those are all my moments. I can then normalize this. Let's just do that. This is actually, I think, the main thing I want to show you. Let's divide this by Q, S, and C, and this is S ref and C ref, where C ref is our mean aerodynamic chord. So do the same here. We'll do the same here. I'm going to write it this way. And then here also Q, S, C. Okay. Yes. I'm not sure that's going to be the easiest way, but let's keep going with this. So this term here, this is the pitching moment about my center of gravity. the definition we saw last time. This is my pitching moment about my wing. Let's just call it W. And then this is going to be X wing over C. And then by definition, this is the CL of my wing. Okay, so far so good. The one thing we have to be careful though is this last term here. This is not CL of my tail, because CL of my tail I need to normalize by the area of the tail and the dynamic pressure at the tail, which is not necessarily the same as the dynamic pressure at the wing. So what I'm going to do, let's multiply and divide by Q tail, S tail. I'm going to put that on top and bottom. And so now this term here is CL of my tail, right? Because I got to normalize the tail by its own properties. That's what we normally would do. So this is going to be X tail times C times, let's say, CL of the tail. That's the part in red. So now I've got these extra terms. Yes. Yeah, actually, I'm going to write this in a different order. Sorry. Let's write this first one first. The CL of the tail. That's the red part. Okay. Then I've got these extra terms here. I've got Q tail over Q wing. I didn't call it wing before. We'll just call it that. Okay, so I've got this term, the ratio of those dynamic pressures. And if the velocity is just constant all the way through, that's going to be 1. In general, though, it's usually less than 1 because the tail is in the wake of the wing. So there's some slower velocities there. It's maybe a ratio of, like, say, 0.9 or something. There might be a 10 or 15% loss in that dynamic pressure. Could be worse, but that's maybe a typical value. If I have a T-tail where the tail is up high, right, then I may be out of the wake, and that could still be 1. But in general, that's just going to be a parameter that depends on the design. And then what I have left is S-tail, and I'm writing the wing W just to be explicit here, and then XT over chord, and that's going to be our mean aerodynamic chord. Okay, so everything looked pretty similar to before, except for I've got this extra term here. By the way, this term here, we call this the tail volume coefficient. It's this non-dimensional parameter, and sometimes it's used for early stage sizing of a tail. We can kind of give some rough numbers about what that non-dimensional number should be to help you initially size the tail. And you can look in the book for some guidance there. There's some numbers there that will help you, you know, we'll kind of do that in one of the next assignments. Okay, so let's see. I guess we could go through the same analysis. It's going to be the same as we saw last time. So the aerodynamic center thing, that didn't change at all. So that stability thing, that was universal. When we did that stability analysis, we had an aerodynamic center. That was for the entire aircraft. So it doesn't matter how many tails or lifting surfaces there are, where they are, fuselage or whatever. All of that was wrapped into one. So here, though, let's just look at having our pitching moment be 0. And I mainly did this thing here so I could show you where that tail volume coefficient comes from. But for the purposes of making this simpler, I'm going to go back to the original equation. We just had just this. L wing minus XT LT, and we need that to be 0 to have trim, okay? And so I'm going to color the ones that are positive green and the ones that are negative red. We know this is negative. We know that this distance here is going to be positive, and the tail for a conventional tail, this is definitely going to be positive, and the lift on my wing better be positive. So that means then that this whole term here is negative, right? Because there's a negative sign in front of it. And this first one is negative. So I need this last term to be positive. So what that means is, since there's a negative sign here, I need LT to be negative, right? And that's what we already just kind of saw from the physical rationalization, we need the tail to be lifting downward, right? So it doesn't have to be a ton because it can be far back there a bit, but it does need to be there. And again, we're going to pay a penalty. We're going to pay, usually that increase in drag that we pay, we call it trim drag, because there's increased drag, both because the tail creates its own induced drag, but that also changes the lift that the wing needs to carry, which increases its induced drag. And we usually put that together and call it trim drag. It's just extra drag we need to trim the airplane out to get it to zero moment. Okay, so the lift of the tail is lifting downwards. Actually, though, this equation points to another possibility. What if the LT was positive, the tail was lifting upward, but we made XT negative? In other words, we put the tail in front of the airplane. So that's another possibility. And this is called a canard. Okay, so here's a conceptual drawing here. So the canard, we could actually have positive lift on the wing and then positive lift on, we don't usually call it a tail in this case, the canard. And so you can see, right, that this is balanced. There's a moment this way, a moment this way. The canard isn't usually as far back as the tail, so it carries a bigger percentage of the load, as opposed to a tail, which is pretty far back. But it can be positive. So this is kind of the maybe one rationale for why this might be benefit, is that it generates an upload, so we're not generating any negative lift anywhere, so the wing actually has to do less. That means we could also decrease the size of our wing a bit because it doesn't need to carry as much lift, so it could potentially be a bit lighter, have less weight, have less wetted area. So this is an appealing concept. In practice, though, it tends not to necessarily come out ahead aerodynamically. It's often just a wash, and depending on how you do it, it could be beneficial, but it could also be much worse. The reason for that is because the canard, we generally, we still have to keep our center of lift, aerodynamic center, behind our CG, so we can't put the canard too far forward. And because it's not that far, it needs to carry a sizable amount of the lift, right? So this term here is pretty big. Whereas for a tail, pushing that further back, that doesn't really, that's not going to bring our aerodynamic center forward. So that's okay. But for the canard, if we put too much lift, if we move the canard too far forward, our aerodynamic center would come forward and be unstable. So it doesn't go that far, but that means to generate the moment that we need, it's going to be a pretty significant chunk of our total lift. What that means is that the wake from the canard is going to be fairly significant, and it's going to cause some interference on our wing. We're going to have lower velocities on the wing, increased turbulence, a drop in lift generally in that region. And so that's going to create some increased drag. So even though the canard was carrying more lift and we needed less lift at the wing, because of that wake, it decreased some lift in the wing, and so we actually need to increase that back, so we kind of lost a lot of that benefit. Another reason that's, we'll see in a second, you actually need the canard, you need to design it so that the canard, this part, is going to stall first. Otherwise, it's going to be unstable. So imagine what happens as I tilt up an angle of attack. Imagine that my wing stalls first. So this lift goes away. Now I've got still the lift of the canard, and I'm going to tip up even further. That's going to be bad. Conversely, let's say I go up and the canard stalls first, so that goes away. Now I've got just the lift back here. It's going to tilt me down, and so I'm going to be stable. But because that needs to happen, because I need the canard to stall first, that generally means I need the main wing to be a bit bigger, right, to give me the CLs that I want. And so those benefits that we said about the canard is that, well, I don't need as much lift because the canard's carrying it, and the wing can be smaller because that lift. They're mostly counteracted because the wake of the canard then interferes with the wing, so I need more lift. And because of the stall characteristics, I actually need to keep that wing pretty big. So in the end, it's a tricky design. There can be cases where it can be good, but it's not the obvious win that it appears. And in fact, in many cases, it can be much worse. So we don't see them as much. However, there is quite a few of these in home-built aircraft, and the reason is related to what we just talked about with stall. is that if you design it right, you can make it pretty much stall proof, right? Because as you increase an angle of attack, if you design so that canard always stalls first, then you're going to move back down, right? So this can be an appealing feature for these home-built aircraft where you may be less experienced pilots flying, and you want to have that extra measure of safety that you're not going to accidentally get yourself in a dangerous stall, that the aircraft has that sort of safety measure built in that it's going to stall and push you back down. So that's what you see here. This is the Burt Rutan's Long Easy. This is one of these home-built aircraft, and it has a canard for that reason, because it's a more pilot-friendly for these home-built aircraft. Okay, so that concludes our discussion on longitudinal stability. Next time we'll start talking about lateral stability.